This video will talk about the characteristic features of ionic compounds. So a couple things to get us started. One, ionic compounds don't exist as discrete molecules. And what that means is if we have something that is a discrete molecule, we have something like water, H2O, and that if I were to zoom in, I would see that I have individual water molecules, two hydrogens and one oxygen, and they would all be acting separately from one another. Now, when I go to an ionic compound, what I see is this kind of continuous array. And we'll look at some images on the next slide of what that exactly looks like. The next thing to note is that the formula of an ionic compound is usually the same as the empirical formula. Now, we'll talk more about empirical formulas later on in the chapter, but what we're worried about right now is that it's kind of, think of it as like a reduced fraction. We don't talk about something being 2/4, we talk about it being 1/2. We still have the same proportions, the same ratio between in case of the fraction, the numerator and the denominator, but we just show it differently. The same thing is true for ionic compounds. So we don't write sodium 1,000,002, chloride 1,000,002. We just say sodium chloride because it's that ratio, that 1-to-1 ratio for sodium chloride, or the 1-to-2 ratio for, say, magnesium bromide that we're worried about. And so what we see because of this, what we have is lots and lots of ions together in a three-dimensional network, a very ordered, structured arrangement of those ions. So here's an example of sodium chloride. There's a couple things we want to notice here when we look at the sodium chloride, and what we see is that in the picture on the left here, we have these chloride ions, these green ions, the larger ones. We have the sodium ions here that are purple, those are smaller, and what we can look at is that we have this continuous array where we have sodium ion, chloride ion, sodium ion, chloride ion, sodium ion, chloride ion, and this continues on, and it continues in all directions. And so when you pick up a grain of salt, what you're really looking at is a very large array of a bunch of sodium ions and a bunch of chloride ions. The key thing is that for every sodium ion, there is exactly one chloride ion, so we maintain that ratio. So on the right, what we see is a little bit of an expanded version. Again, here's our chloride ions are the larger ones. Our sodium ions are these smaller blue ones. And we see this array. And so they kind of spread the atoms out to make it a little easier to see how they're arranged. What's on the left is a more accurate representation of how those ions are arranged. So just two different ways of looking at the same thing. So how do we figure out what the formulas are? How do we know that sodium chloride is NaCl? Why one sodium and one chloride? When we go to something like magnesium chloride, now it's one magnesium and two chlorides. Why those ratios? And where that comes in is when we start looking at the ions that actually form. Because what we find is that when we look at most of our main group elements, they will either form a cation or an anion, and when they do, they will form those ions with one possible charge. And so we have to worry about the number of electrons being lost by our cations and gained by the anions, because those two numbers must be equal to make a neutral compound. So, ionic compounds are formed from the combination of at least one cation and one anion. Now, we can have multiple, or we might have two different elements represented, but have multiple atoms of those elements, or multiple ions of each of those elements. The key thing is that we want to be electrically neutral. We have to have a neutral compound, otherwise it's not an ionic compound. And the way we get it to be electrically neutral is we use those subscripts to balance the charges. So the total number of electrons lost by all of the cations is equal to the total number of electrons gained by all of the anions.